If you know the product of any reaction, it's very hard to fail the mechanism. Like, why would you? This is going to be the first video about heterocyclic synthesis, and we're going to talk about the Arno, Dano, and Hash-Widman synthesis. And before talking about these ones, you should be familiar with these reactions and the mechanisms, because they are applicable. We're going to apply them in these mechanisms. Please don't forget to subscribe, like the videos, and share. Let's go. We have this reaction of this is a ketone with a primary amine. We shall form imine, and this imine can tautomerize, form an amine by tautomerization. How can we write the mechanism? If you have a ketone and it is acid catalyzed reaction, we have a ketone, we have this R2 and R1. This one, R1, just shows that it can be a different substituent, and this one can be a different substituent. Then we have this. This oxygen has lone pairs of electrons. It will attack the proton. So when it attacks the proton, we shall have this. R1 and R2. Then we have this with hydrogen, and it's a positive. Now, as it tries to stabilize this primary amine, NH2 with R, nitrogen has lone pairs of electrons to attack this carbocation. So when it attacks the carbocation, we shall form this. We have R2, R1, then this is OH. Then we have N, H, and R. So let's name this one R3. Okay, R3. It can be any substituent, but attached to the amine, so to the primary amine. Then, but this one is a positive charge, so it is unstable. Here we shall have a proton shift. Forming this compound. R2, you have R1, then this one will be OH2. Now this one is plus. Then the nitrogen stabilizes. So we have NH with R3. This is what we have. So nitrogen is having lone pairs back. It's having lone pairs back to form a bond. As it forms a bond, this one will break off. When it breaks off, we shall form this. We have R2, R1, then here we have this N, H, and R, but it is a plus. We're having this. So we shall lose a hydrogen or a proton, forming R2, then R1 with N and R. So this is imine. This one here is imine, but this one can tautomerize, form this. So this nitrogen, here we have hydrogen, of them. We can lose one hydrogen, form a bond, then nitrogen takes back the bond, the electrons from here. When it takes the electrons, it can take now this hydrogen which is lost, so forming this. We form N with a hydrogen and R, and we have formed a bond here. Then we have R2 and R1. This is R3. So this is enamine. This is enamine. So that's the mechanism. We want to see this mechanism because we are going to apply them in synthesis of these heterocyclics using Aldol Hodge's reaction. Now, that's one. We have this. This is a keto. If you have a keto, this keto can tautomerize. Remember, we have a hydrogen here. We have 2 of them, hydrogen here and here. So this one, oxygen will pull electrons towards itself. Then we shall lose one of the hydrogen form a bond there. So we shall have this R1. We have R2. Then we have O minus with a bond. And this hydrogen can be taken by this very oxygen atom and form this. So this is keto and this is enol. Enol. This is E. So this tautomerization, we shall see them in our synthesis. That's the second reaction. Then we have this reaction, Aldol reaction. It's Aldol reaction. If you have a ketone, now here we are having 2 ketones and a base OH. It's a nucleophile. It's a nucleophile now. So the mechanism will be you're having R2, you're having R1 upwards and oxygen atom. Here, this carbon is saturated, so you're having 2 hydrogen atoms. This oxygen, this OH group is a nucleophile, and oxygen is having lone pairs of electrons. So it will attack one of the hydrogen. When it attacks the hydrogen, these bond electrons are given to this carbon atom. So we shall form this with R1, R2 I mean. Here we are having R1, oxygen, and we're having lone pairs on this carbon. So it is having high electron density. So this one is now a nucleophile, but you can have tautomerization. This oxygen is more electronegative, so it pulls electrons towards itself. As it pulls electrons, it's forming a carbocation here. So this one will form a bond there. So shall have this R1, then oxygen minus with a bond and R2. This is what we are having. So we have used one of the ketone. So let's use the second one. This one is a double bond and it's having a lot of electrons. So we bring the remaining ketone. R3, R4, and we're having oxygen atom. This oxygen is also electronegative to pull electrons towards itself, creating the carbocation. So as this one brings the bond back, we are forming a double bond, then this one will attack this carbocation because you are forming a bond with this carbon. Then this one uses these bond electrons to attack this carbocation. So we shall form this R1, R2, and oxygen atom. Now here we have formed a bond R3, oxygen is minus, and R4. Then this oxygen can get proton from water molecules, so it can attack this one. So we shall form this R1 oxygen, R2. Then we are having a bond here, R3, then OH and R4. Still deserving lone pairs of electrons. It will attack more water. So we are forming the OH back. We are forming because this hydrogen breaks off from the water. So we shall have this R1, R2, this oxygen, and this R3, R4, and H2. And this one is now unstable. It is unstable. Remember, we have hydrogen atom here. So this hydrogen atom breaks off and forms a bond. When it forms a bond, this one breaks off. So you have R1, oxygen, R2, and we're having a double bond now, R3 and R4. So this is Aldol reaction. Aldol is a structure where we're having a ketone, then separated by alpha carbon with the OH group. So we're having here a ketone with a OH separated by the alpha carbon. So we're having this carbon separating the ketone and the OH group. But it can continue to this. This is enone. This is enone. We are having oxygen and alpha carbon, then we form a double bond. So this reaction is reversible. It is reversible. Now, this is the mechanism. This is the mechanism. Now, we are having this. We are having this mechanism here, where we are having this conjugated to the diketone. This is the diketone. And this one is our enone. So enone conjugates to this to form this one. Let's see the mechanism. We are having this. We have a diketone with R2, R1. Now, this one, the ethane will act as a base. Remember, we're having two hydrogen ions. So it's like this mechanism. We are having the OH, which is a base acting as a nucleophile. It's the same thing here. This oxygen is having lone pairs of electrons. So to attack the hydrogen, this one will give the bonds to this carbon. So we shall have this. This is R2, R1. So we shall have lone pairs here. So this one is a nucleophile. It has a lot of electrons. Now, same thing. As one of the oxygen pulls electrons, this one can form a bond. So we shall have this O minus R2 here and R1. So it's a resonance. It's a resonance. Bring our enone. We're having R3 and O here. As this oxygen pulls electrons toward itself, we are creating a carbocation. So this one forms a bond here. creating a carbocation. Now, as this oxygen brings back the electrons, remember here we had formed a bond. Here. This bond will attack the electrons here, will attack this carbocation, forming this R2, R1. Then you're forming back the oxygen, and you're having this oxygen. Now here we have formed this with O minus, and we have a bond here and R3. This is what we are having. Now, as this oxygen forms back the bond, this one will attack hydrogen. So we shall form R2 oxygen, then we form this. So that's the conjugation. And here you're having R1. R can be any substituent, but it's a diketone having alpha carbon. So that's the mechanism. Now we are good to go. Talk about this synthesis.